Bien, merci de votre...
Well, thank you for being loyal to this series of lectures. Last week we did nuclear all day, and we sandwiched nuclear with a lecture about eco-design, and just after that today, something about bio-inspiration. So you see that we're perfectly politically correct. That's not the reason why I put this lecture here. It's because the entire course was constructed around the rationale of from materials encountered by chance to materials made to measure, with the very specific ways in which you can fill in the gaps in material space, and filling in these gaps by using all sorts of methods, such as combining different types of materials or different geometries, which is what I called architectured materials. And we're now looping the loop of this course with bio-inspired materials. I'm going to tell you about natural materials and how analyzing these natural materials can help to develop ideas for new materials to further fill in the gaps in the material space. So in a sense, we're really looping the loop because there's nothing more encountered by chance than natural material, and there's nothing more made to measure than an architectured material. So today's lecture is really in conjunction with the seminar that follows and the workshops this afternoon. It's really going to reflect the fact that it's a changing discipline. Obviously, I'm not going to cover all of its aspects in only 1 hour. What I'm going to do this morning is to tell you about inspiration that can be drawn from materials that are going to be solicited statically. John Dollop will then, from Potsdam, will then give you the seminar, where there's a group who were working on biomimetism, and we'll talk about dynamics, not only the materials themselves, but their actuators. And this afternoon we'll have a workshop around a certain number of issues inspired by nature. We'll have a presentation about diffuse interfaces. They're not necessarily strict interfaces. There might be benefits in these diffuse interfaces. We'll have a talk about how we can design bio-inspired materials, one about the biomimetic aspects that you can have in various devices, drones, olfactory sensors, and so on and so forth. And this afternoon we'll illustrate a whole set of different situations in which inspiration from nature is important. I would like to say that it's inspiration rather than imitation, which are quite two different things. And we're trying to find in natural solutions ideas that can help to develop materials. So there we are, right up here at the right, and we've covered all the rest. So I'm going to start by telling you about a particularly efficient engineer, the spider. When the spider makes a web, it has a certain number of functions. I'm not going to tell you that spiders are particularly smart animals. I don't know how many neurons they have. I think, isn't there an entomology expert in the room? I think it doesn't have very many brain cells. But it can make some pretty clever things. If you look at a spider web, it has at least 2 functions. One of it is to hang properly to the branches of the trees, but it also needs to dampen the shock when a little fly hits the web in order for it to be captured. So we have our good old contradictory friends, solidity and energy absorbent. One of the engineer's nightmares in the automotive industry, for example. So the spider solves the problem by using the same polymer throughout. This polymer, same chemical composition in red here, to make the outer beams, as it were, to ensure the solidity, and then it's going to use a highly crystallized material in order to do this. And for the part of the spider web which goes round in circles, which is in blue here, it's a polymer, but it's much less crystallized. And you can see here the 2 traction graphs of the various bits of... So, in fact, what we do is that we pull little bits of spider web, and you can see that the blue one has a very low rigidity, but very high deformation, allowing it to absorb much energy. And the red part is extremely rigid. So, in a sense, this is the way in which a smart engineer would have solved the problem. You can't have a single material to do both, so you can fine-tune the geometry of your material in order for it to fulfill what you would like it to. So after this little idea of weighing flies with a spider web, let's first have a look at the principles of natural materials. And we'll then see how, based on these principles, we can try to solve or circumvent contradictions in specifications, which is a leitmotif in all of this course. It's how you can combine contraries, how you can ask a material to do things that it naturally can't. The principle of natural materials are, of course, there are characteristics in terms of characteristics, but also in terms of elaboration. Biological materials have very few elements composing them, and the way in which they develop is essentially through growth, which is biologically controlled, and usually through self-assembly processes. You have local rules, and then the elementary bricks build onto each other, and it results in something that has an approximate design and that more or less addresses the function. If you look at engineering materials, you have all of Mendeleev's table, so great variety of materials, and it is manufactured from melts, powders, solutions, in order to obtain an exact design. If you look at what this implies in terms of processes, biological materials have low temperature processes. They're mandatory, in fact, because they're essentially therefore limited to polymeric engineering and solution chemistry. On the engineering side, you can use pretty much all sorts of temperatures with some pretty violent processes, and the evolution of materials over history, as I showed in the first course, is very much linked to the available energy, the temperature that could be reached, which has opened up new ways to use materials in engineering. So there are bridges, of course, between the two that already exists. What is called soft chemistry. Clément Sanchez is working a lot on that. We're trying to develop artificial materials with bio-inspired chemistry that avoids these very high temperature processes. As I said in the inaugural lecture, what I'm trying to show is that there are material creation processes that try to make very large amounts of material for a very small cost, which is typically the question for a structural engineer who needs tons and tons of material. So if I continue the parallel, this is a nice picture given to me by Peter Fratzel, the parallel between a Ford T, a high-tech object where they're perfectly identical and follow the plan, and this field of sunflowers. Of course, they're not entirely identical, but there's a single genetic code that allows them to look likely. If an engineer had made sunflowers, it would be less pretty because they'd all be exactly the same. And if nature made Ford T's, I'm not quite sure, we'd have something very easy to repair because it would never be exactly the same shape or size. First principle we're going to examine, common to all biological materials, is that they have a hierarchical structuring. The key part of the microstructure in the understanding of materials' properties. As regards biological materials, you need to think in terms of microstructure at many, many different scales, with a hierarchy, much more than in artificial materials. So there's a hierarchy of structures at pretty much all level, all scale. If you look at a tree, if you start looking inside the tree, you have the wood cellular structure, Inside you have each of these little rectangular cells, which are each formed by a composite structure made with a matrix and a cellulose fiber, which is wound very evenly around the cells. The way in which it is wound, the volume fraction of each of the cells, the angle at which it is spun and wound is absolutely not neutral. It's controlled, in a sense, or at least it responds, addresses the needs, the function, depending on the position on the branch, depending on the fact that the wind is reacting to continuous wood, for instance. First example of natural structure. And you'll have a talk this afternoon that will tell you about something that is both concerns wood architecture. Wood is more or less dense. The winding angle is more or less sharp, and the mechanical properties are different, and that allows you to understand a certain number of actuators. It's one of the aspects that John Dunlop will probably also tell us about. Now, if I look at something from another very smart animal, the turkey, you see, spiders, turkeys, all sorts of very, very smart animals. If you look at a tendon in a turkey, you start to look at it and you said, this is starting to look very much like a cable. It's a cable of a cable of a cable. And you have a whole architecture which can go all the way down to the nanometer. All the way. The case of bones is also very interesting. This is a healthy femur. You can see that the ostrobecula, what's in it, is not hollow. When you age with osteoporosis, the bones hollow out. Osteoporosis, that's what it is. Obviously, it doesn't work so well when you have a hollow bone, because eventually it snaps. And for the vertebrae, that's why kids grow and adults shrink, because you accumulate and compress the vacuum formed. So at least this type of bone is formed of cellular material. We've seen cellular materials as examples of architectured materials, and it has exactly the same elemental bricks, which result either from solution chemistry, hydroxyapatite, or organic materials, collagen, and you're basically going to have exactly the same result. Either you'll have the cortical bone, which is the bone around it, or the inside oat, and the trabecular bone is the more porous material inside. Now, if you zoom in, again, you have a multi-scale configuration where inside the kind of bone foam, each of the walls of these little foam cells is formed of a lamellar structure. The lamellar structure is a combination of fibers, which are themselves a combination of platelets, of mineral particles, and collagen fibers. So you have a number of ideas that seem to appear very naturally. In fact, every time you have all of these scales that stack one over the other, one interesting thing is every time one of these phases is fragile, we try to make them as small as possible. Damage resistance, which is another nightmare of the engineer, is concerned here. So, what are the main benefits of scaling down, of having smaller, fragile sections? This is an emblematic example of biomimetic materials. Look at the oyster shell. It's a fantastic material. Every time you eat an oyster for Christmas, you can notice that it's very tough, and and you can actually cut your fingers when opening them. In fact, we have a calcium carbonate here. It's actually not stable carbon. It's not neutral, the fact that this calcium carbonate should be in presence of proteins between the layers. Is quite a very interesting chemistry there that's actually not understood very well. But from the brutal point of view of the engineer, you have a set of platelets which are fragile, which are pre-fragmented. Starts to look like what I was telling you about interlocking materials, and they're sandwiched with organic matter, which is not very rigid, but which has a very high energy dissipation capacity. So when you want to crack that, the crack ends up all bogged down into the biological material, because it absorbs energy, this protein fraction. And the crack's energy is dissipated very efficiently. So if I look at bones, from an engineer's point of view, it's quite unsettling, because red here you have collagen, low modulus, very high energy absorption capacity. Blue rather, is mineral, as any mineral substance. It has a high modulus, but it has low energy absorption. And when you have a bone, it's in fact better than you would expect by simply mixing the two. So obviously mechanics is more subtle than just mixing two things in heterogeneous environments. You know how to create a certain number of landmarks where you're expecting a particular composite. Meaning that what we've done is that, in a sense, we've modified the properties of the constitutive material simply by integrating it into the composite in the manner in which you do this. One of the vision of the composite effect could be encapsulated like this. I think it's quite interesting in how Potsdam has examined biomimetism. It's to try to simplify things as much as possible, not just to describe the mechanical properties, you just need to have adjustable parameters for that, but to draw from your understanding of the mechanisms a few simple principles that are going to allow you, at least on paper, to develop interesting new materials. One of the things that was done was to note that the structure you have in composite is essentially formed of soft and hard matter, and what you have here is an aspect factor. You have a length that is much longer than the width. If you look at a composite such as this, you have some very rigid elements and a matrix which essentially transmits shearing. And you can see that the modulus of the composite is essentially the shearing modulus of the matrix, which is low, corrected by the aspect factor between the length and width of the element. If you take bone or dentin, which is what constitutes your teeth, you can have a factor of 10 to the power of 4 between the shearing modulus of the polymer and the traction modulus of the composite. What you can draw from that as an engineer is you can be in a situation where if you have a very powerful aspect factor, you can have a much higher modulus than the modulus of the lowest, of the weakest part. Second thing, this is truly mechanical. People who work in mechanics hate scales, and physicists hate limit conditions. But beyond that, if you look at the scale, imagine that there is a crack in the hard part, the grey part here. I take a crack, which is length A, and if I want to calculate the amount of stress it can withstand, I will say that it's essentially dissipated energy required to propagate that. So you have interface energy with a rigidity modulus, which must be divided by the crack length. What we're just trying to say here, in terms of physics, is that when you have a crack that is of length A, what allows you to propagate the crack if you're releasing elastic energy, that happens within a volume that varies as a square of the crack length. And that's going to vary with the length of the crack. So you have one that varies like the square and one that varies like the length, and you're going to obtain a length below which it does not propagate and above which it does, and it depends on the elastic energy that is stored. If you have a lot of force, it's short. It's exactly the same as if you pop a balloon with a pin. If it is very much inflated, it'll pop. If it is not very much inflated, it'll just leak air gently. So this type of formula says that if what you're given is the material's rigidity and the surface energy that must be created to propagate the crack, why is it essentially a surface energy? Because the material is essentially fragile. The stress that you're going to need to apply for the propagation, if you have a crack that is at least not bigger than the element, well, that constraint varies as the reverse of the square root of its size. So for a fragile material, the smaller it is, the greater the constraint it can withstand, for two reasons. The first one is what I've just explained, propagation of a crack existing in the material. And the second reason is that if it's small, there's less volume, and if there's less volume, there's less chance that a crack will appear. So you need to make things as small as possible. So you essentially have two ingredients in the constitution of structured materials that can withstand damage. You have a material that is made of organic substance that can absorb energy, and inorganic to provide rigidity, as long as it is small in size and has a very high aspect factor. So I've just slightly exaggerated, but explained in a sense why bones, why wood, why mother of pearl shells can be interesting in terms of damage resistance, damage tolerance. So once you've done that, you have another scale. I've only talked about one type of architecture, one scale. Here I actually can't really go into very much detail, but the basic idea here is that when you're making a composite of a composite of a composite of a composite, when you have a whole hierarchy of architectures, you end up in a situation where cracks are always subcritical versus the scale above it. So the crack will propagate very, very slowly, allowing you to have damage tolerance that's particularly effective. These are ideas that have been very much developed by Gao. Just another image, a multi-architectured lamella structure that's very damage resistant. I actually like it as an old bachelor. It's called the love cage. It's a structure that's given as a wedding gift to people who are about to marry in Japan. It lives in symbiosis with two shrimps that are trapped inside it. It's not very good fun. I think that's why it's a wedding gift. It's extraordinarily... an optical quality of the glass is amazing. It may have an influence on the reproductive mechanisms of the shrimp. It's very good optically, but then of course glass is not very damage tolerant. And in fact this structure, this cage structure, is cabled. It has beams and cables, and each of the beams is an onion peel structure. There are a great number of successive layers of glass layered with organic material, meaning that this material is particularly tenacious. So this is the example of a silica rod, a normal rod, perfectly. You can just run it through a platinum mold, and then you can take the same glass structures with one of these onion peel structures, and you will see in terms of the breaking point and so on, the difference. So let me now return, now that I've just looked at living materials. I've looked at them as if they were dead, wondering why it works so well. Now we're going to do something else, which is a little bit more subtle, and which in a sense poses a number of problems is we're going to look at living biological material that's alive and how it grows. One of its characteristics is that the system can adapt when there is a low variation in the conditions. See, imagine if you have a bridge, when there's a flood, you have the feet of the bridge that will swell. What you do is that you build them. When you build a bridge, you try to factor that in. Make sure that the bridge won't be swept away. What's interesting in nature is that, in a sense, if the variations are not too brutal or extreme, there can be an adaptation. Evolution is not the right word, but there can be an adaptation of the structure that is in the making. So, don't confuse the Eiffel Tower and a tree. They essentially have the same function. It's to climb as high as possible with a minimum amount of material in order to not buckle under its own weight. So in 1889 it was to show how clever we were, and to have a tree is to go up as high as possible to catch the light as much as possible. Basically it's the same purpose, mechanically. So the result is to say we need to find a material where the root of the elasticity modulus divided by its density is maximum. You want to go as high as possible with a column structure which must not buckle under its own weight, which very quickly brings you that, in fact, the best material to make a tree is probably wood, which is not really much of a surprise. But one thing that's interesting is that you may imagine a tree growing. So, you know, this tree is just growing there, unfettered. You can see it here if it's growing in a coastal area with a lot of wind, and there you develop a certain number of structures. You have roots that are bigger on one side than on the other. The tree, in a sense, develops its own substance to adapt to outside stress and solicitations. It can adapt to these unpleasant conditions as long as they're not brutal. If there's a hurricane, the tree's uprooted. So the adaptative growth of the tree. Let's have a look at another way that this can happen, which I think is very, very pretty. It's how you can play with the architecture on the level of the cell. You have these cells here, which are a fibrocellulose composite with this filament wrapped around each of the cells. So if you're in mechanics, if you want something very rigid and very easy to deform, you again have your schizophrenic engineering problem. You think it's not going to work properly, because if you want high deformability, if you want to pull the cell, you would want your wire to be wound this way, but if you want it very rigid, you would like them to be positioned in the same way as the pulling. So if you want wood that's very flexible, you need, if you look at the stress axis, you need to have something that's perpendicular to that. And if you want wood that's very rigid, you're going to try to wind that along the axis. It's something that can be measured. There have been experiences carried out by an Austrian team consisting in X-ray diffraction in a situation where essentially using the same experimental tools as what is used in metallurgy. You can measure the crystalline orientation of the cellulose fibrils, and you can actually take each of these little cells and measure the elasticity modulus and deformability. Easier said than done. These are micro machines. There are micro machines that can allow you to do that. You're pulling on sort of little micron hairs, but depending on the fibril spiral direction, where the angle is close to zero, meaning that it's as close as possible as the traction axis, you have low deformability and high modulus, and when the filaments are wound more and more in the circumference of the cylinder, you have a low modulus and high deformability. So you think, as a professor in materials mechanics, this is great fun. If you take the branch of a tree, the interesting thing is that the only thing that's alive in a tree, it's only the edge. In the branch you have a history of the tree. People who do climate history love it because it allows them to know how what the interval between summer and winter was 600 years ago. But here we're just going to take a branch picked up by the Austrian scientist who is going to be measuring the cellulose microfibril angle distribution. The situation we have today is that the external part of it, the branch, has 0 to 10 degrees. So it's a very rigid part, and as you move away from the upper part, you have a fibril spinning angle, which is around 40-50 degrees, something very flexible. So if you look at this tree there, the tree branch, if you look at the rounds, the circles in it, you can actually have if you can have the history of its life. That was what it looked like 5 years ago, 8 years ago, meaning that 8 years ago, the branch in this Austrian spruce, in a place that's full of snow, it's growing in order to have the capacity to bend when the snow falls upon it. So you need to have something flexible. And gradually, as the branch grows, you end up in a situation where it needs to bear more and more weight, it needs to extend further and further, it needs to withstand snow more and more, and you're going to in a situation where it's going to need to be increasingly rigid. So what you have here is functional adaptation with the growth of the object, adaptation to the structure in the smallest scale to obtain this type of growth. So that's the tree solution. The bone has another solution, which is not to adapt the finest architecture, but to adapt the highest architecture, meaning that for bones you're going to adapt in terms of the cell structure and not in terms of the assembly between mineral and organic substance. So if you look at a bone, again, that's something else which people in mechanics find completely fascinating. Nothing new, this interest in natural solutions. It's what has been called the Wolff's rule. He had very rightly said that a bone was a Gothic cathedral. It was in the name where structure calculations were done almost by hand and not with computers. And the way in which the Eiffel Tower was calculated, essentially. And you had a few histology exams. You see where there is mineral substance, where there isn't, and if there's a structure where you look at the forces in the same way as the flying buttresses help to transfer the forces, the stress. Well, what happens in a femur such as this is that there are also lines with the highest bone density. So basically this mineral substance has been deposited just precisely where it was needed. I don't really believe in a particular finality, but this seems to work very well. I told you about osteoporosis. This is a vertebra, someone who's 27-year-old, and that's a vertebra of a 97-year-old. I thought I could show you that because there's also gender equality. You know, osteoporosis also happens to men. It's just that it tends to occur later in life. You see, it's almost empty. It's almost ready to collapse. What has happened is that here there's a dynamic balance that makes it possible to spread the bony material in a sense to address, to answer the load to which the vertebra is subjected. If you think of a baby that has just been born, and just paddled around in the placenta for 9 months, G equals 0, no, floating in water. Wonder why they actually bother to come out at all. But babies, baby bones are essentially isotropic. And then, of course, gradually, they've just discovered this thing called gravity, and the bones start to structure and to spread the mineral substance around in order to address outside solicitations, outside stress, which is not very violent, except when they're actually born. And then gradually they're going to move around, they're going to start running, and the bones are going to grow to respond to muscular effort, which is why when you send astronauts up in space, I'm sure you've always wondered why they sit around space stations cycling or running around. It's not just to keep them busy, it's just because they would tend to be empty, to lose their mineral content, and if they come back to Earth they break, and you can't break astronauts, they're expensive things. So they need to have this force to kind of force them to organize the material to withstand an external force. So what actually happens microscopically? It's not that clear, but I'll give you a version that would probably make doctors scream. It's really an engineer's approach. There are 3 types of cell. I'm sure that John will correct me if I'm wrong. You have osteoblasts, which deposit the mineral substance. You have osteoclasts, which remove the mineral substance, because minerals is something very precious in human beings. So the trick that bones use is to place the mineral substance just where you need it. He's not just saying, okay, I need to go and get some outside. It works by a local recycling. So that's what osteoblasts do. Osteoclasts destroy. They take the mineral substance where it's not needed, and the osteocytes tell the blasts and clasts where mineral substance is needed or not. So essentially you have a structure. So obviously this can be connected to the piezoelectric properties of hydroxyapatite, but there's a signaling structure that's not that easy to comprehend. You have cells that have the capacity to say where there's stress and where there isn't, and to carry the substance from where it's not needed to where it is. If you think about it, you think that's pretty smart. But engineers are pretty smart too, because this is typically the kind of approach engineers use when they're trying to create optimized structures. You have your finite elements calculation, you see where the stress is and where it isn't, and you move around the material from one place to another. It's typically what engineers do. You can actually look at what's happening in a bone to try to imagine methods to make aircraft lighter. So the parallel between bone and wood, they're both structured materials, probably not only structured materials actually. The bones are of course structured materials, but they're also a calcium reserve. So I think you need to be wary of finalist approaches, because you can always say that it's perfectly optimized, but in fact we don't really know why. As a specialist said, the bone is a solution to a problem, but what's the problem? How you can adapt a structure and architecture based on outside stress. If you take the bone, you have a resorption deposition of material, an adaptation on the tissue level, meaning in the porous structure itself. And if you take wood, you only have deposition of new material, and adaptation occurs on the material level, in the exact shape of the composite. Which brought us to identify a few essentials in the structure and production of these natural materials. Of course, this only happens through gentle chemistry, no brutal chemistry. So let's look at resolving contradictions, which have very much been the leitmotif of this course. Let me show you this fine picture of bridges. I love bridges, probably because I don't like walls. A nice picture of a bridge here. What I wanted to show you is a page from a cable catalogue. What construction engineers use if they want to, build a suspension bridge. There are pages and pages and pages of different cable architectures. We didn't wait for bio-inspiration to create architecture systems. It's actually quite interesting for people who have a curious mind. These cable architectures are actually approaches that are very often empirical. To try to have a scientific approach that's not empirical but purely mechanical is something that still needs to be further explored. So just to show you this fine picture of a bridge and to tell you that there's plenty of things that could be done. It's not just civil engineering that should have been solved 150 years ago. Still hasn't completely. So let's look at my favorite contradiction. We want something that's strong and damage tolerant. I know, it sounds like I'm a bit obsessed with that, but this is one thing that we saw. The first solution we had a look at was this sponge structure, where we had a multi-layer solution. Here the organic glue between the various layers. And this is another multi-layer structure. It's the kind of thing you can do either on the solid material with an indentation, and then you have the lamella material underneath, and you can see that you have something that's absorbed much more energy in order to do the indentation. Now, what I wanted to show you, the rationale behind that, is that if you take a crack and try to propagate it through this multi-layer structure, there are two effects you need to bear in mind. There's one effect, you can have a very weak interface, in which case the crack is going to try to deviate. And that's what people who make ceramic composites that can withstand high temperatures. Another example of extreme materials that we could have discussed but didn't. But essentially, ceramics are very rigid, works in very high temperatures, but is unfortunately fragile. If you have a ceramic composite with fine structures and a great number of interfaces, if there's a crack in there, it won't. It'll have very long propagation paths because it's just going to follow the easy interfaces. And that's how you can obtain plasticity, the damaged plasticity. It doesn't snap, but it just gradually breaks, leaving you a little bit of time and absorbs lots of energy by doing this. Another solution would be to stop the crack by having a very low modulus. The energy that allows the crack to spread is that's lacking in the elastic energy, but it doesn't have to. Now, what I would like to show you is, can engineers be smarter than oysters? Which would be quite reassuring when you look an oyster in the eye. It doesn't look very bright. So there are a certain number of very interesting potential strategies. One of those could be a microstructure gradient. That is the tooth strategy. If you take a tooth, you have a hard, soft, and hard structure. The hard structure makes it wear resistant, and the soft structure allows it to have cracks that do not propagate because, again, they get stuck in a zone, an area that dissipates energy. If you take a milk tooth, the hard part is very thin and the soft part is very porous. If you take a wisdom tooth, you have a relatively low porosity part because it grows pretty slowly. But it's the same materials, the same elementary blocks. So how can that be done as an engineer? You take a steel with a lot of carbon, place it in hydrogenated argon. You take the carbon from the steel and you end up with a decarbonated layer on the surface, and therefore a soft layer. And you've even changed the phase because you now have a decarbonated layer on the surface that's ferrite. And there you can change almost any microstructure you like to have something that's very hard in the middle, pretty soft on the surface, and damage tolerant, because surface damage does not propagate to the core. You're just limited by the size of your oven here. What you can do is actually recarbonate the outside so you can have hard, soft, hard. That would be a way of making ball bearings that are both very hard, that can withstand heavy loads because the core is hard, but that are very wear resistant or damage resistant because the crack can't propagate. So it's a way of making a fragile material more ductile. So that can be done not only in chemical terms, it can also be done in terms of microstructure. That's the trick, known as SMAT, Surface Mechanical Attrition Treatment. It's a surface treatment that's quite brutal, not necessarily at room temperature. And you can have a copper part, for instance, a lot of deformation, overblasted, where you have high elasticity limit and high ductility. Here in black, you have the classic curve, the classic graph of work-hardened copper. The more it's work-hardened, the less deformable it is. Again, the engineer's nightmare. And in red, you have the same material where a surface layer has been applied, where this kind of hyper-blasting, and it's compressed, and therefore that's going to prevent crack propagation, and it's kind enough to considerably increase the rate of work hardening. When it deforms, it finds it more difficult. So again, a case in which you're trying to play not on the constitution of the material, but on a gradient of microstructures. So you have seen another strategy, which is that of architecture design, when you try to have an influence on the forms, on the shapes. Here another very smart animal, the tortoise. I was telling you about the tortoise shell, which is also a interlocking material. It needs to be flexible and solid. The animal must breathe. The solution, what you do is you fracture the plates in order to prevent crack propagation, but done in a smart way so that the different bits hold together. And say that between these different plates, these different components in the architectured material, different components of the architectured material, as I said, you can have something, you can include, for instance, an elastomer with a plexiglass to absorb the energy. You can change the condition of friction between the various blocks. That would be another solution to try to make a made-to-measure material. I was telling you about polymers, but it would be quite interesting to do this with intrinsically fragile materials, to have structures that can work in high temperatures. Before I yield the floor to John Lunlop, I would just like to discuss biomimetism in structured materials. I would just focus on structured materials. We could probably do the same exercise with optical properties, with butterfly wings. There's vast amounts of literature about all that. I did it on the structured properties because that's what was basically covered in this course. What I wanted to show you was not how to find the best material to produce a tree. We know it's wood, but based on an analysis of the efficiency of the materials used to make wood, or to make bones, to try and find a few simple principles to give us product development guidelines. It's a very trendy thing at the moment. A diagram of the number of papers per year. If there are lots of papers, it means lots of people are working on it. It's attracting a lot of people. It doesn't necessarily mean it's interesting, it's not proportional. But actually it is. So obviously it's very difficult to read all of the papers that are published, but if you use observations of materials and try to find the principle in it, it actually allows you a better understanding of the objects you're going to be creating. So of course the Holy Grail, as you will have understood from all of these lectures, what we're really trying to do is to combine the variety of engineering materials with the flexibility of natural architectures, notably its capacity to have hierarchy. We would love to create new materials with radically new properties. We would like to fill multifunctional requirements. It's essentially what we saw at the start of the course. It was the roadmap. How do you move from the material encountered by chance to the made-to-measure material? That's precisely what we're trying to do with, as a plus, the fact that you want to produce them in large quantities at affordable cost. So technological innovation for the Scots, or for the people from the Auvergne. I am myself from the Auvergne. So you can end up in a situation with a combined approach, combining classic materials science, which is essentially acting on the microstructure, with the classic mechanics to try to influence the structure. And I've showed you, both in artificial materials and in natural materials, situations in which there are gradients of properties, or situations in which you have architectured materials. What do they have in common is that the spread, the distribution of the microstructures or geometries and local properties varies along a length of scale that's comparable to at least one of the scales of the component you're considering. So this is pretty much the playing field that is offered in trying to produce made-to-measure materials. What appeared in terms of natural materials is that there's a multi-scale hierarchy, that there are adapted processes for multi-materials. That's what nature does, and what perhaps we can imagine that we could do. You're going to see one case where it can be done by using specific solidification processes. I told you about the soft chemistry, gentle chemistry processes, surface treatments in metallurgy. It's possible, but now there are two aspects which have emerged quite specifically in natural materials, is that they're materials that can self-heal, and that engineers are not necessarily very good at that. We saw in durability one example where it could be done through slackening of a polymerizing agent within a composite that contained capsules. There's a well-known case developed not very far from here with self-healing elastomers. A very interesting case, but it's still, this is really on the cutting edge of R&D. It's not standard in the use of materials. And materials with adaptive growth is something that we can't really do yet. But if we don't have long-term objectives that are not necessarily easy to reach, but point the way for development, if you don't want to have these, you're better off being a banker. So a few caveats. You need to be careful of the Abbé Pluche syndrome. The Abbé Pluche was one of these lovely scientists of the 18th century. L'Abbé Pluche very seriously said that God had created melon in quarters so that people could eat them, so that a family could eat a melon. The problem with bioinspiration is not to say everything's perfect. Nature has had everything right, and it's exactly what I need. That's why you need to have this abstract concept of materials in order to develop new ones, in the same way as you pass through the microstructure to try to optimize it, to know where you need to act to improve the properties. You need to abstract from the natural material the principles to allow you to develop artificial ones. Mysticism is not allowed. Men succeeded in building aeroplanes when they stopped thinking of flapping their wings, because that simply didn't work. It's very important to think in terms of inspiration rather than imitation. And the key point that can make a lovely dream into a reality, I think, from an engineer's point of view, is the process. What are the processes that can allow us to develop these materials? And that's really something that is a hot topic in the manner in which we can import new ideas from biomimetics. Just 3 little pictures to finish: a bird's nest, a monofilament material in steel, and the microstructure that was on the poster of the Collège de France lecture. Thank you very much for your attention, and I shall now yield the floor to John Dunlop for the seminar. Thank you very much for attending so consistently.